Hello, I'm Jonathan Wien, and in this video, we're going to walk through a classic calorimetry problem. Okay, so in a coffee cup calorimeter, 100 milliliters of 1 molarity hydrogen chloride acid is mixed with 50 milliliters of 1 molarity sodium hydroxide. The temperature of the solution rises from 22 Celsius to 29.5 Celsius. Assume the specific heat capacity and density of the solution is the same as water, and that the heat capacity of the coffee cup is 23.5 joules per Celsius. Part A, calculate the amount of heat released in the solution. Part B, identify the limiting reagent and calculate the number of moles that reacted. And part C, determine the enthalpy change per mole reaction. So this question also gives us our balanced equation. So let's first write out our givens. So right here, I did 100 milliliters of 1 molarity HCl, 50 milliliters of 1 molarity NaOH, and our temperature change was 22 Celsius all the way to 29.5 Celsius. Our specific heat of the solution is 4.184 joules per grams times Celsius, due to the fact that it's the same as water, and our density of the solution is 1 gram per milliliter, due to it being also the same as water. Our heat capacity of our calorimeter will be 23.5 joules per Celsius, and then with our givens, we can do the first part of our equation by using the MCAT formula. This is the MCAT formula. So Q is telling us how much heat is produced. M is the mass of the solution. It has to be in grams. C is the specific heat capacity of the solution. And delta T is the change in temperature. So we know that to find the mass, we multiply it by the density and volume. So let's put that in the equation, knowing that our density and that our volume is the sum of our two reagents. Oh wait, no. Let's put that in an equation, knowing our density and that the volume is the sum of our two reagents. So here's our density. Here is us adding our two reagents together volume-wise and multiplying it. We should have gotten this in grams, which will be our mass. And this allows us to move on to temperature change, which we subtract the final temperature. Subtracting the final temperature by the initial temperature, sorry. And we should have gotten this as our answer. Now we can plug all these values in the MCAT formula. This is our mass. This is our specific heat capacity, and this is our temperature change. We should have gotten this, and after dividing it by 1,000 to get kilojoules, we should have gotten this. Now we need to find a limiting reagent by multiplying the two reagents' molarities and volume in liters to get their moles and converting them to a product to see which would make less of the product, which would be the limiting reaction. This is because we're moving on to part B, identifying the limiting reagent. So we should have gotten this. As you see, we multiplied molarity and volume in liters to get the moles and turn them into NaCl, which is a product. And this process showed us that NaOH was the limiting reactant because it made half the NaCl, as shown here, compared to the other reagent, HCl. Now we're moving on to part C, where we have to find the enthalpy change of the reaction, and this is found with this equation right here. first one. So we need Q of the reaction, which we'll find using this formula. And we already have Q of the solution, so let's find the Q of the calorimeter using the equation where C is the heat capacity and T is the temperature change, which is the same as the solutions. So we can plug in our given heat capacity multiplied by the temperature change. And we should have gotten this, divided it by 1,000, and gotten this number in kilojoules as our Q for our calorimeter. Okay, so we can find the Q of the reaction now. And as a reminder, it's the negative of Q cal plus Q solution. So looking at our Q cal a few minutes back, it should have been this plus this, which is our calorimeter Q, and the negative sign, which should have produced this in kilograms. I mean, kilojoules. And we now have the Q of the reaction, and to find the moles of the reaction, we need to find the amount of moles we have in our reaction, but this reaction only needs 1 mole of each reagent, which makes it so that it would just be the amount of moles in the limiting reagent. And we already found out that, so we can plug it in right here with this being our Q reaction and this being the amount of moles in our limiting reagent, which can be converted to moles of the reaction in just a 1-to-1 ratio. And we should have gotten this as our change in enthalpy for one mole. And that should conclude this question. And thank you for watching.